Hello, everyone. Good evening. Three shots. Shailaja, I'm Sydney. Yes, good evening, everybody.
Good evening, sir.
Yes. So, are you all ready? Time is exactly 5. Maybe we have almost 9 people. We'll wait for 1 or 2 more minutes, right, for people to join and start. Right. So, we are almost at the verge of completing periodic table chapter as I told yesterday. Right. So, I might be requiring just maybe 15-20 minutes for today. Right. And next chapter would be chemical bonding. Right. Okay. And I have a homework for you, right? So I want you to do all the book back problems of periodic table and submit it to me before the next class, right? I mean, next class is not tomorrow's class, next week's class. Okay. We didn't do problems as such, but by the way in which I taught the chapter itself, it actually, like, I took problems means they will just ask you, they'll give you 4 or 5 elements, right? And they'll ask you to arrange them in the order of ionization energy, or say electron gain enthalpy, or say any of the atomic trends for that matter, right? So first thing you have to know is the element is present where, which group it belongs to, right? After which element that particular element comes, right? All these things. Once again. Yeah. So what I was telling, yes, that's how problems will be asked. Okay. Or then the questions might be like define electron gain enthalpy, right? Or the questions might be like even though fluorine is more electronegative, right? Why is it that fluorine is having more electron gain enthalpy, right? All these type of questions, all the exceptions are very important. We saw so many exceptions. We expect something to happen, say along the period, down the group, it increases or decreases. But for 2 of the elements alone, there will be some mismatch. Okay, right? So those kind, why is it happening? All the things we discussed, not even one point was missed. Okay, I don't know how many of you are taking notes. If you have taken notes, you just have to go through the notes. It will take 5 minutes for you to go through the notes before your exam, like for this particular chapter. Okay, if at all you have not taken down notes, whomever has taken down notes, please get it from them, right? But this is not a fair thing for them because they have taken notes, they spend some time, right? But you are just, getting the work done very easily. Ask them. If they say okay, then get it. Okay, it is going to be very useful. And from on, at least from the next chapter, right? From the next chapter, please have the habit of taking notes. Reading your book will take a lot of time, right? If the word by word you have to read, you write it in a way which you will understand very quickly, like say shortcuts like that, something you write, whatever comes out of your mouth, at least whatever I write on the OneNote which you see, right, must be there on your notebooks. Not for me, obviously for your benefit. It will be easy if at all you want to study the chapter again. Going through your book every time is really a waste of time. Okay, right. So I think now we have enough people. We have 10 people, 11 people with us. I think we can start right away. Right, let me share my screen. Okay, so we spent a lot of time on the electron gain enthalpy. Why is it positive? Why is it negative? And when I go down the group, whether it becomes less positive, more negative, all these stuff, all these things. What do you mean by it is becoming less positive and more negative? All these things we saw last class, right? And we even saw an exception for fluorine, oxygen, sulfur, and nitrogen, phosphorus. You can remember this 3 groups, like 3 pairs, where I expect fluorine to have more, but actually fluorine has more. Why? Is because of high charge density for fluorine, and there'll be high interelectronic repulsion. The incoming electron will suffer repulsion because there are already so many electrons existing in the very small space for fluorine. That was the reasons, right? Okay, for today, so moving on. So last class I forgot to write the name. So this is 11th. I'm not write the name because the date is already there. Okay, right. Now, moving on, there is only one atomic trend left. Okay, that will try to address. Right. Okay. So yesterday we saw about electron gain enthalpy. So the last, last atomic trend which you're going to see is, why is it? 1 second, people. Okay. Right. So the last one is, what is my electronegativity? Right. So how we had electropositivity, this is my electronegativity. Again, this electronegativity can be combined or studied together with this non-metallic character, right? Or we can study it with ability to get reduced or ability to be an oxidizing agent. This is exactly how we saw for your electropositivity. Exactly opposite things we saw, but I think you're able to correlate how all these things are again connected, right? Okay, so now we'll first try to understand what is electronegativity now. Then we'll go slowly to all this stuff one by one, right? Okay, now the term electronegativity, how will I define it? Right, it is defined as the ability of the element to attract shared pair of electrons towards itself. Right? This is the perfect definition I can give for electronegativity. Right? It is the ability of the element to attract a shared pair of electron towards itself. Okay. Now, from the, like, if at all I have to, again, we'll come back to this definition, right? But if I have to make a layman understand, if at all there's no science student, right? But I have to make them understand what exactly is electronegativity. I can tell it in this way: it is the ability to accept electron and form an atom. Right? This is a very decent definition I can give, but that's the perfect definition, right? It is the ability of the element to attract shared pair of electron towards itself. That's the perfect definition. But if at all you want to understand what exactly is electronegativity, it is nothing but the ability to accept electron to form an anion. Obviously, to form an anion, you need to accept electron, right? What is the ability? How easily it accepts? More easily it accepts, more is the electronegativity. That is how it is. Okay, now spending some time on this particular definition I gave you, ability of the element to attract a shared pair of electron towards itself. Now, what am I trying to say is that people, generally we speak electronegativity in terms of compounds. How do I put it is, say for example, let me consider H2 molecule, okay, a hydrogen molecule. Now I know I have a bond between H and H. Is it not? I know this is a normal covalent bond, correct? I have one electron coming from this, one electron coming from this, getting mutually shared, isn't it? Right. So now if you look into where this two electrons are present, okay, where these two electrons are present, if you ask me that question, I will tell that there will be some nucleus, right? This hydrogen will have some nucleus. This hydrogen will have some nucleus. Okay. Now the electron density, right? The two electrons are going to be present exactly at the center of these two nuclei. Is it not? Between this hydrogen nuclei and this hydrogen nucleus, these two electrons are going to get shared, and it is going to be at the exact center of these two nuclei. Okay, but if you take a case where I say I have HCl or say I have HF, right? Now what is going to happen is that, say for example, forget about HF, we'll see, come back later. Now if you look at the HCl, now again I have a bond, right? Now these are again, say, one electron coming from this, another electron coming from this, mutually shared, a covalent bond is formed. This one all we know already, right? How a covalent bond, like we'll speak about it in detail when we go for chemical bonding, but still now you know for a covalent bond to be formed, one electron to come from each of the atom, right? So one electron comes from here, one electron comes from chlorine, right? Now, if you check where this electron is, where these two electrons are present, right? Last time you found that they are exactly at the center. Okay, but this time, what will you see is that, say, if this is the point where the center is, now the electron cloud, these two electrons will be there more towards chlorine. Okay, these two electrons will not be at the center, right? Now, those two electrons will be little away from the center and they will be more and more towards chlorine. Okay, they'll be more and more towards chlorine. Why this happens? Now this is what. So now you look at the definition. It is the ability of the element to attract a shared pair of electron. Now this is the shared pair of electron you're talking about, right? This is the shared pair of electron is mutually shared from the covalent bond. Okay, now this chlorine, what is it going to do? It is highly electronegative. That means it has the ability to attract these two electrons towards itself. If this element was not electronegative, then it would have been like the previous case. The electron would have been exactly the center. The two electrons would have been exactly the center. But now, since chlorine is electronegative, or I would say in more correct words, since chlorine is more electronegative than hydrogen, right? Since chlorine is more electronegative than hydrogen, these shared pair of electrons will be more towards chlorine and little far away from hydrogen, and it is not going to be at the center. Okay, now this ability of attracting the shared pair of electron towards that particular element, that term, the ability, is what is called as electronegativity. In short form, I can write it as EN. Okay, right? Or you can simply say that, say, Cl will accept an electron to form Cl minus. What is the ability of this reaction? What is the feasibility of this reaction? Obviously, that is also going to be electronegative. But the perfect definition is this: attracting a shared pair of electron towards itself. Okay, right. Now, since chlorine is electronegative, the same thing will happen in Cl2 molecule. Cl, if I have this bond, now tell me whether again there are two electrons, right? One electron coming from this chlorine, another electron coming from this chlorine. Now think about it and tell me whether these two electrons will be at the center or not. Will it be at the center or not?
Yes, sir.
Yes.
It will be at
Yes.
center, sir.
Why? Why is it at the center?
Sir, electronegativity is
Both
same
are
in both.
equally electronegative.
Correct. Exactly, right? So this chlorine obviously will try to pull the electron towards this side. This chlorine also will try to pull the electron towards this side, but these are same chlorine atoms, same amount of electronegativity. So at the end, what will you see is that the electron will still stay at the center. Okay, so it depends. So now remember this. Okay, now you will again see this in chemical bonding. Whenever you see that the electron cloud is at the center, okay, now those kind of molecules are what are called as non-polar molecules. Okay, or non-polar compounds, I call it. Okay, Cl2, H2, Br2, O2, all these things. Okay, all these are non-polar molecules. But whenever you see there is a shift from the center, right? The electron cloud is more towards one element and little far away from the other element. Whenever you see this is happening, these kind of molecules are what are called as polar molecules. Polar molecules. Okay, now what do you mean by polar in general? Polar generally talks about charges. Is it not? When I say polar, North Pole, South Pole, like positive poles, negative poles, something like that if you see, right? So it's always about something to do with some charge. Okay, now how charges are associated here if you check, right? Now, if the electron is at the center, right? If the electron is at the center, no problem. There are no charges here. Overall, it is neutral. I mean, every molecule is overall neutral. Okay, but if the electron is not at the center, right? If the electron cloud is not at the center, what it is going to happen is, say, if it is in the center, I told you it is neutral, but something negative is moving towards you, right? Something negative is moving towards you. Obviously, that will induce some negative charge onto you. Is it not? You are neutral, right? But something negative is coming towards me. So obviously it will induce some negative charges onto me. The same thing will happen in this case also, right? So since the electron cloud is moving more towards chlorine, now you will see that the chlorine will have a partial negative charge. When I put this del negative, if I put this represents a partial negative charge. Now, why am I developing a partial negative charge? Is because the electron is not at the center, it is moving towards chlorine, so that will induce a partial negative charge on chlorine. Okay, now again, what you have to understand is you have to maintain charge neutrality. Overall, the compound is still neutral, right? Now, how can you account for it? Obviously, the electron cloud is moving away from hydrogen, right? Now, that will induce a partial positive charge on hydrogen. Okay, that will induce a partial positive charge on hydrogen. Okay, now in none of the non-polar molecules you will see this charge separation. This particular phenomena, what I'm talking about, is what is called as charge separation. Okay, charge separation into like partial positive and partial negative, and this is happening because of one of the element is more electronegative. The electron cloud is moving towards that more electronegative element. Okay, right. So that is going to induce this partial positive and partial negative charges. So whenever you see this partial positive and partial negative charges, these kind of molecules are what are called as polar molecules. We'll speak about this particular thing in depth when I go to the next chapter, but just now introducing to you.
Sir?
Okay. Yeah, tell me.
Sir, can you give me example for a non-polar compound?
Yeah, anything. H2 is a non-polar compound. Cl2 is a non-polar compound. Say I can tell Br2.
Sir, actually, Cl2, H2, these are diatomic molecules, right? They are not compounds.
Same doubt, sir.
They are diatomic molecules and not compounds.
Yes, sir.
Yes. So generally, when I want to make a compound, I need to mix two different elements. That is the thing. So now if I have to ask you a compound which is not polar, I'll give you this one. Say if I have I have to give you an example. Say I take beryllium chloride. Okay, BeCl2. Okay, now you can look at this. Now say the electron cloud, like say again, you have to consider two different bonds here. This bond separately you have to consider, and this bond separately you have to consider. Okay, so again you will see two electrons, two electrons, two electrons, two electrons. Now the electron cloud will be moving towards chlorine. This side it will be moving towards chlorine. Again, you will see the end result. End result is nothing. End result is that the electron cloud will be at the center only because they are pulling towards each other. They are pulling towards each other. Or I would say this also is not a good example. Let me take, for example, methane molecule, CH4. Okay, now you see I take one CH bond. I have 4 CH bonds here, obviously, right? There are 4 CH bonds here. You take one CH bond. Okay, now say obviously carbon, hydrogen, the electronegativity difference is there. Say carbon might be more electronegative than hydrogen. Possible, right? But the difference in electronegativity is not that much. Right, the difference in electronegativity is not that much. So the charges you produce here, say del negative and del positive, are almost tending to zero. Almost tending to zero. Why? Because the electronegativity of C is approximately, I would say, sometimes little equal to hydrogen also. Okay, so this bond is not polar, even though there is difference in electronegativity. Okay, even though there is different electronegativity, but the partial positive and partial negative charges produced are almost negligible, almost close to zero, because the electronegativity difference are very close by. Okay, but if you have huge difference in electronegativity, like say fluorine and hydrogen, chlorine and hydrogen, or H2O molecule for that matter, I have a OH bond, right? These are highly polar bonds. Now, let me give you this point also. When I say polarity, when I talk about polarity of a bond, right, it is directly proportional to the difference in electronegativity, not the electronegativity. Okay, it is directly proportional to the difference in electronegativity between the bonding atoms. Okay, between the bonding atoms. right? So more and more is the difference in electronegativity. One is highly electropositive, one is highly electronegative. In those kind of cases, the polarity of the bond is very huge. When I say polarity, I'm talking about the charge separation. Amount of del positive and amount of del negative will be huge. It will be more and more increasing if the difference in electronegativity between the atoms is also keeping on increasing. But as the difference in electronegativity between the bonding atoms becomes smaller and smaller and smaller, the bond is going to go more and more towards non-polar nature. Okay, hope did I answer your question?
Yes, sir. So if the difference in electronegativity is very less, then polarity of the bond will also be less.
Yes, correct.
Sir, but then polarity still exists, right?
Polarity still exists. Actually, there is a scale. Okay, there is this scale. Yeah, Pauling scale, which says that if the delta En of AB, in the sense that that means the electronegativity difference. Okay, electronegativity difference is greater than 0.7. Okay, if the electronegativity is greater than 0.7, then I can call the molecules as polar. If it is less than 0.7, no, it is called non-polar molecules. It's like that.
Okay, sir. Between C and H,
exactly. It is lesser than 0.7.
Yes,
sir. Sir,
okay. Yeah, tell me.
Sir, is every diatomic molecule a non-polar?
If it is a homonuclear diatomic molecule, what do you mean by homonuclear? Same atoms coming together to make a diatomic molecule, H2, Cl2, O2, like that. If you have, definitely they are non-polar. You can blindly say, right? Okay. But if they are heteronuclear diatomic molecules, HCl, HF, H2, not H2 is not diatomic, anything like HBr, all these things. Now, NaCl, for example, right? All these are polar molecules. Hope you understand what I'm trying to say.
Yes, sir. Understand.
Yes. Okay. Good. Okay. So that is what is about electronegativity. Now we have to understand how it varies down the group and how it varies along the period. Oh no! Like actually, we have to speak how all these things are connected now, right? So we understood what is electronegativity. Right now, obviously that is connected to the non-metallic character, because I would say generally non-metals are electronegative in nature. That is how we define non-metals itself. They generally will form negative ions. Is it not? Right? Non-metals will generally form negative ions. So obviously that is why we correlate non-metallic character with electronegativity. Okay, and I think these two will be able to easily understand ability to get reduced. Obviously, right now, if they want to form your negative charges, right? Say, for example, if Cl has to form Cl minus, it has to accept an electron. Is it not? Now, yesterday itself, I told you, gain of electron is reduction, loss of electron is oxidation. Right? Again, I repeat, gain of electron is reduction, loss of electron is oxidation. Right now, you see chlorine is accepting an electron or gaining an electron. So obviously this entire process is nothing but reduction. Right? Okay, that is why we say it is the ability of the element to get reduced also by accepting electron. Right? And obviously, if something is getting reduced, that will definitely be an oxidizing agent. Okay, that will definitely be an oxidizing agent. I think this all this all makes sense. Exactly similar to electropositivity, what we did there. Right? Okay, fine. So now we'll try to understand how electronegativity is varying down the group and along the period, right? And it is going to be exactly opposite in the opposite of electropositivity. Is it not? Right? So now En along the period and down the group. Okay, along the period and down the group, we'll try to understand how it varies. Okay, now please understand, along the period it increases. Right now, if you can remember what happens for electropositivity, you don't have to remember this exact opposite thing will happen. Right, it is all about how easily I'll be able to add an electron to the valence shell. That's all about it. Okay, so along the period it increases. Say now, that's why again we say when I go from the left hand side of the periodic table, right? If this is the periodic table, left hand side of the periodic table is fully metals, but the entire P block are non-metals. We already spoke about this. Is it not? Because as I go from left to right of the period, metallic character decreases, non-metallic character will increase, or say electropositivity is decreasing and electronegativity is increasing. Okay, right, fine. Now, obviously, down the group, it is going to decrease. Electronegativity decreases, right? And from this, you can get you 1 point for sure. Fluorine is the most electronegative element in the periodic table. Okay, fluorine is the most electronegative element in the periodic table. Obviously, right? Because you start with lithium, you go, obviously at the end you have fluorine, and obviously along the period it increases, right? But when I go down the group, it decreases. Obviously, this is the point where I have maximum electronegativity. Okay, right? So I think these are all the things which you have to know about electronegativity. And as far as the chapter is concerned, your periodic table chapter, the chapter is done. Okay, is there anything I missed, like from you learned, sir, you missed this point, anything you want to add? Did I miss anything? Is everything covered, guys? Is everything covered? Did I miss anything? Did I miss any point? Yes, no? Or you only don't know what and all is there, right? That is the
Everything is done, I guess, sir.
everything is done, right? So you still have, I can still talk about this terms called as hydration energy, how it varies down the group and all along the period, all these things. But this hydration energy, how is it varying and all, we'll see in chemical bonding, CB, as well as in thermodynamics. In both of them, we'll try to understand how this hydration energy or solvation energy increases down the group along the period, all these things we'll see. Okay, that's the only thing which is not there. But again, that will be like, I don't know whether that is there in this particular chapter, in periodic table chapter, but that is there for you, I know, like in some chapter, whether in chemical bonding or thermodynamics, it is definitely there, and that time we'll see. Okay, anybody has any questions, people, from this chapter? Anybody wants to ask me anything? The chapter is done, that's it. Anybody wants to ask me anything?
Sir, what is dielectric constant?
What is dielectric constant? Okay, fine. That's a physics term, but still I can look into it. Do you know anything about capacitors?
Capacitance, I know. I don't know what it is.
What do you say?
Capacitance.
CAPI, capacitors. Do you know anything about this? Have you heard this term capacitors? No? Yes. I think there's a problem with my mic. Is everything okay, guys? Are you able to hear me?
Yes, sir.
Sir, are you able to hear me?
Yeah, now I'm able to hear you. Tell me. Yeah.
Yes, sir. I don't know about capacitors. I know about capacitance.
Nothing. Okay. Capacitors has capacitance. Nothing else. Right. Basically, when I want to define what is capacitance, I would define it as ability to store charge. That is what is capacitance. Like capacitors are the one which stores its charge. Okay, right. So now the capacitance, like how you have resistance symbol like this, you put something like this, right? For resistance. For capacitance, we put the symbol like this. This is capacitance, this is resistance. Two parallel lines we draw, and that is what is capacitor. That is resistor. This is capacitor. Right. Okay. So now, what do you want to know is this, right? Say now, what is a capacitor made up of? It is basically made up of two plates. These are two plates. Plates in the sense they are conductors. Okay, they are conductors. Okay, and what you have to understand is one of them will be positively charged, right? And the other one will be negatively charged. Okay, one of them will be positively charged, the other will be negatively charged. Okay, so now in between these two plates or in between these two conductors, there'll be some medium, right? There'll be some medium. Say it can be air or it can be water. It can be anything, whatever you want it to be. Okay, it can be anything what you want it to be. Okay, right. So now, every medium, like if it is air, if it is water, they will have different properties, right? So one of the properties of each medium, one of the property is what is my dielectric constant, right? So now, if you want to look at the value of capacitance C value is epsilon A by D, right? Now A is the area between the parallel plate. Okay, between these two plates, what is the area between them? That area, and this D is the distance between these two. Right, the entire area is A, and the distance between these two is D. Okay, now this epsilon is nothing but is what is called as your dielectric constant. Okay, now this is a property of the metal which will like, how do I put it? A dielectric constant talks about the ability of the medium to make sure that the charges are able to flow through it, right? So very high dielectric constant means the charge will not be able to move through it properly. A very less dielectric constant, then it can move through it very easily. That's how it is, dielectric constant. Okay,
sir.
dielectric constant basically talks about the ability of the electron or some charge to move through that medium. That is what is called as dielectric constant.
Sir, or that is conductivity, right?
Not exactly, but still, yeah, some you can tell approximately, yeah, conductivity, yes, but not exactly. Right? You will get a more crisp idea when you go to 12th class. 12th class physics, you go, there's a chapter called as current electricity. I think it's your third chapter in CBSE. Right? At that time, you will get to know all these formulas. What is dielectric constant? What is C? What is capacitor? What is parallel plate? What is series split capacitor? All these things you'll study in your 12th class. Okay, right? Fine. Any other questions anybody has? Okay, so if that's the case, I think we can go to the next chapter. Shall we? What is the time? Yeah, I took half an hour. Right then. Okay, so the next chapter is one of the most important chapters, not with respect to marks, but again with respect to knowledge. Yeah, please tell me.
Sir, I went through the book yesterday. I forgot to tell that along with the gaseous atom, it was also included isolated gaseous atom. Yes, sir.
Isolated gaseous atom, right? Obviously,
Yes,
it makes sense. As I told you, why we even take a gaseous atom is because I want the atoms to be very far away from each other. I don't want any one atom influencing the next atom in any other way, right?
Yes,
so that's the reason why they say isolated gaseous atom. Gaseous itself is okay, but when I say isolated, it is perfectly isolated gaseous species. It's like that. That's the only reason. Nothing else.
Sir, ionization energy is calculated only for single atom.
Obviously, like ionization energy, electron gain enthalpy. Oh, wait. But thing is, they will obviously the unit is joule. But if you look at the unit, they'll mention it will be joule per mole, kilojoule per mole.
Yes, sir. Yes,
they will, right? Now, what does this mean is that for one atom they'll calculate. Okay, for one atom they'll calculate, but in 1 mole I will have 6 into 10 to the power 23 atoms.
Yes, sir.
Correct. So whatever the value you are seeing for every element, right? That is the ionization energy of this many atoms combined together, right? If at all you want to get the value for one atom, whatever the value you have, say 7,000 joules or 6,000 joules or whatever it is, you divide it by the Avogadro number. Now you'll get it for one atom value. How much is for one atom value?
Okay, sir.
Understood? Right?
Yes, sir.
Now there is a reason to this. Why we do kilojoule per mole? We'll study about this in thermodynamics again. Very important point. Why do we do this? Why we don't directly use kilojoule? That's a unit of energy, obviously. But why do we divide it by number of moles? There is a very good reason behind this. We'll speak about this when we go for thermodynamics. Right. So I think is everything okay? Now shall we start our chapter? Next chapter, guys.
Yes, sir.
Right. I hope everybody is ready. Right. Oh. Chemical bonding. Right. Fine. Okay. Right. So as I said, right, this chapter is important not only for marks, right, but for you to appreciate chemistry, right? Now, this is the first chapter. You will actually see how a bond is formed. If a bond is formed, what is the structure of the bond? And if there are so many multiple bonds together, what is the shape of the molecule? Right? You told that, say, I know CH4 is going to be, I don't know whether you know this, you must have learned in your 10th class that all carbon molecules are tetrahedral in shape. Did you study? Did you heard this term tetrahedral?
Yes, sir.
Okay, so yeah, so these kind of things, how this is tetrahedral, what is tetrahedral shape for that matter, like what are the other different shapes any molecule can take, right? Now you will understand, if I complete this chapter, now there are only going to be, say, 10 or 11 possible shapes available for any molecule to take. Okay, and any molecule, whatever be the molecule, will fit in any one of these 10 shapes. Okay, now all these, what is the theory behind it, and why only those are the only possibilities and not anything else, right? And you must have known the concept of something called as bond strength, right? Say, I'll tell that HF bond is stronger than HCl bond. Why is it like that? Right? Why is it that HF bond is stronger than HCl bond? Right? And say, right? So now I know water, if I take, right? So water has something called as hydrogen bonding. Other than the normal chemical bonds you see, right? There are so many other secondary bonds, I call it. Right? So many non-covalent interactions. When I say non-covalent interaction, I'm not talking about a proper bond. I'm not talking about a proper covalent bond or ionic bond. I'm talking about some kind of interaction which can be having. Right? How is it that so many atoms are able to exist together? Right? How is it that so many, or say, if I take one tumbler of water, right? If I take one tumbler of water, I know I'm going to have millions and millions of water molecules. The water molecule is very small, H2O, like 2 hydrogen atoms and 1 oxygen atom, right? How is it that so many H2O molecules are able to stay together, right? Not only for H2O for that matter, how any atoms, or how is it that so many atoms and so many molecules are able to exist together? Right? All these questions we will try to answer in this chapter. Very basic. We go to the very root of why is a bond forming, first of all, right? And second thing is, if a bond is formed, what is the other parameters we can look into, how strong the bond is, or say there are something like bond angle, bond strength. How do we determine all those? Yeah, tell me.
Sir, so it's all related to the structure, right?
Yeah, it is all related to the structure, obviously. But
Then
yeah,
what,
I will go in. Yeah, tell me.
why is it not coming under physical chemistry? It's coming under inorganic.
Oh, no, what happens is how a bond formation happens, right? Those and all should come under physical chemistry, right? But analyzing the parameters, giving chemical reasons for that, why is it that HF bond is stronger than HCl bond, and looking into the shapes of the molecule, right? All these things will come under inorganic only, right? We don't use any physics here. It is all purely in terms of chemistry. That's why we don't go for physical chemistry in this. But sometimes, right, some books, for example, if you take Ranjit Shahi and all, Ranjit Shahi chemical bonding chapter will actually be in physical chemistry. Right? What you said absolutely makes sense. It's not only you who thinks like that. There are other people also who thinks that chemical bonding should come under physical chemistry. But again, doesn't matter whether it's there in physical or inorganic. All you have to understand is why this chapter is very, very important. Very, very important chapter. And you will be using these things till your 12th class. Okay, whatever I'm going to teach you in this chapter, you will be using them till your 12th class for sure. And obviously, if you go to college, maybe if you continue with chemistry, obviously you'll be continuing there also. Okay, right. Fine. So now what I have to understand first is, what is a bond? When I say a bond in chemistry, what do you mean by that? Okay. Now, in very simple words, a bond is nothing but some kind of attractive force. Okay. A bond is nothing but some kind of attractive force which binds two atoms of same thing, or say one atom of one element, another atom of some element to be together, or say I have two compounds, one H2O molecule, another H2O molecule, how they're able to stay with each other, right? Anything which talks about an attractive force, anything which binds two substances or two atoms or two molecules, that particular attractive force is what is termed as a bond. Okay, so when I say a bond in chemistry, it talks nothing but an attractive force which exists between two species. As simple as that. Okay, now second question is, why a bond? Why is it that elements come together or atoms come together to make a bond? Why are they making bonds? Why is it that if they are just sodium and chlorine are away, why I mean, what to say? If you keep them in contact, right? If I keep sodium solid and chlorine gas in contact, why is it that they are undergoing a reaction to form NaCl? Basically, a bond is formed between Na and Cl. Why is it like that? Why are they forming a bond? Right now, with the answer to this question, I think we have already answered this. Why a bond is because I want to gain stability. Okay, why a bond formation happens between two atoms? It's because both the atoms will gain stability by making sure that they form a bond. Okay, so if someone asks you why a bond is formed in chemistry, you tell that atoms involved in bond formation are going to get stability, and that's the reason why they make a bond. Very, very simple. Okay, so two questions. What is a bond? A bond is nothing but an attractive force between two species. And why a bond is formed is because the atoms involved are going to gain stability. Okay, now these two things, if you remember, then we can move on. Right? Why a bond? What is a bond? Then moving on, what are types of bonds? Right? What are types of bonds we have in chemistry? Right? I would say any bond can be broadly classified into two types. Okay, one are what are called as primary bonds, and the other one are what are called as secondary bonds. Okay, one are what are called as primary bonds, the other one are what are called as secondary bonds. Okay, now for me to understand what is a primary bond and what is a secondary bond, I have to go back to Dalton's theory. Okay, now what did Dalton tell about a chemical reaction? What was the postulate of Dalton regarding a chemical reaction? What did he say there? Anybody knows? During a chemical reaction, atoms
Get reorganized.
Correct, right? So he said there will be some kind of rearrangement in atoms during a chemical reaction. That's very simple statement he said. Okay, atoms will undergo some kind of reorganization or some kind of rearrangement, right, during a chemical reaction. Obviously, during a chemical reaction, what happens? During a chemical reaction, some bond breaks, some bond forms, right? Okay, so now whenever a bond is broken or whenever a bond is formed, I can just derive certain things from him. So whenever a bond is formed or whenever a bond is broken or whenever it is coming to a bond, either formation or breaking, there is some kind of rearrangement happening in the atom. Okay, now think about it and tell me now, in atom, like he didn't know what he was talking about, obviously, right? But now we have the knowledge with us. Okay, so think about it and tell me, what is the rearrangement are we trying to speak here? Are we trying to talk about? In atoms, what kind of reorganization or what kind of rearrangement is taking place during a bond formation or a bond breaking? What is happening to an atom? Or what I would say, where exactly is the rearrangement or reorganization taking place inside an atom? What exactly is happening? Can someone add some points to this?
Different shells of the atom.
You're coming closer. Can you Tell it correctly.
Electron.
Electron, what? Electronic configuration.
Electron.
Very, very simple, right? The rearrangement is happening where? The rearrangement is happening in the electronic configuration of an atom. Is it not? Electron is lost, electron is gained, electron is shared, right? Exactly. That is exactly where the rearrangement is happening. Okay, either in the form of addition of electron or loss of electron or sharing of electron. Something is happening to the electronic configuration of an atom when a bond is formed or a bond is broken, for that matter. Okay, right. Now this we understood. We have some kind of rearrangement in the electronic configuration of an atom if a bond forms. We'll talk about bond breaking later. Okay, when a bond is formed, there is some kind of rearrangement happening in the electronic configuration of an atom. Absolutely true. Right. Now, this we understood. Now it is very easy for us to understand what are these primary and secondary bonds. Okay. Now, please understand, a primary bond will have a complete rearrangement in the electronic configuration. When I say EC, right, it is electronic configuration. Okay, so whenever a primary bond is formed, there is complete rearrangement in the electronic configuration, in the sense that electron is completely lost or completely gained or completely shared, for that matter. Okay, that is why we say by complete rearrangement, completely lost or completely gained or completely shared between two atoms. Right. Now, in the case of secondary bonds, secondary chemical bonds, right, I will say that only partial rearrangement takes place. Right? Only partial rearrangement takes place, in the sense that electron is not completely lost, right? It is still somewhere near the atom only, but it is like what to say, it's in the vicinity of the atom, but it is not completely lost. Or say the electron is coming inside, but it is not exactly going inside the atom fully, it is somewhere nearby, that kind of situations. Right? I hope you understand what I mean by partial rearrangement in electronic configuration. Okay, this is a complete rearrangement. Okay, or I would say these are the proper bonds which you already know, right? So we know what are the different types of bonds we have in chemistry. I have something called as an ionic bond, where an electron is completely lost or gained, depending on whether it's a cation or anion. Or I can have covalent bonds, right? You must have studied this also. Or I have something called as coordinate bonds. Have you heard of this term, people? Coordinate bonds?
Yes, sir.
Yes.
Okay,
Sir.
don't worry. If anybody has not heard about it, I will see in this chapter what are these coordinate bonds. Right. So ionic bonds, covalent bonds, coordinate bonds. I have metallic bonds, or I would say metallic bonding or metallic bonds. All these during any of the bond formation, ionic, covalent, coordinate, metallic, in any of these bond formations, there will be complete rearrangement of the electronic configuration of the atoms involved. Obviously, two atoms will be involved, right? For a bond to form. Both the atoms, there will be complete change in the electronic configuration. Okay, right. Now, when I move on to secondary bonds, what are the different types of secondary bonds you have? You have something called as dipole interaction. Okay, I'll write properly. Dipole interactions. Dipole ion interaction. I don't know, you must have learned about van der Waals forces. Right? Under van der Waals force, I have so many. I have London dispersion forces, so on and so forth. But everything is van der Waals force. Okay, the logic is very common. I mean, how? What is the science behind it? What is the logic behind anything? Like is very common. There will be subtle differences between different types of van der Waals force. We'll not go into the detail. Don't worry. Okay, now, and the most important secondary bond which we will be studying is this hydrogen bonding. Very, very important. We'll study about the last of the chapter, but not now, right? But very, very important to understand. If at all anybody in biology here? Any biology students?
I have taken
Ah.
biology.
Right. So in biology, you good. If you study about proteins, if you study about DNA, RNA, right, all the hereditary things which are there in our body, their hydrogen bonding and all is very important.
Biomolecules chapter.
Absolutely. In all biomolecules, proteins, amino acids, peptides, DNA, RNA, nucleic acids, all these things, right, where their hydrogen bonding is very important. Okay, you will actually get a glimpse of this hydrogen bonding in biomolecules in your 12th class. There's a separate chapter in chemistry only, don't worry, right? In chemistry only, not only biology students, everybody will study this. There's a chapter called as biomolecules, the chemistry of biomolecules. So we'll study them, and at that time you will be able to understand how exactly hydrogen bonding is so important in our body, inside body, inside our cells. Every day this hydrogen bonding is happening. Okay, we'll start first. Before moving on to all those, you have to know what is a hydrogen bond, what are the conditions in which a hydrogen bond can be formed, and what conditions it cannot be formed. All these things should be there in our fingertips. Then only we can move further. This is the first step. That is the next step. Okay, right? So now, as I told, primary, secondary, complete rearrangement, partial rearrangement, these and all are the bonds which will come under primary, where I have complete rearrangement, and all these things will come under your secondary bonds. We'll study about all of them in this chapter, all the whatever I've written here on this page, right? Metallic bonding will not study much, don't worry, right? Again, I'll just tell you what metallic bond is, obviously, but we'll not go in depth. But the first three will go in depth, and all the other thing which we wrote here will go in depth and study about them. Okay, right? Fine. So now we will concentrate first on this ionic bond first, and then like I would say most of the chapter, I would say 60 to 70% of the chapter talks about covalent bonds. Right? The initial part of the chapter talks about ionic bonds. Okay, and I would say this coordinate bond which you're seeing here is a form of covalent bond only. It's a special type of covalent bond. So this also comes under covalent bonds only. Okay, so 60% of this chapter talks about covalent bonds, and say the starting of the chapter alone will talk about the ionic bond. Ionic bond is very simple. There is nothing much to understand there, right? But covalent bonds are a little complex. How they are formed, what is the structure, what is the shape, geometry, all these things we'll try to understand. Metallic bonding, I'll just tell you what is this. We'll not go into detail. And that last part of the chapter, you will study about all these things, the secondary types of bonds. Okay, I hope the flow is very clear. What are we going to study? What are we not going to study? Everything is clear with you. I have given you some idea now. Right? Okay, what is the time? Right. Okay, we still have almost half an hour. Right. So we'll move on. Right. We'll move on to study about this ionic bonds today. Okay. Now ionic bonds, as I told you, they are very simple to interpret, very simple to understand. Is it not? Now I told you bonds, when I say a bond is nothing but an attractive force which binds or bounds the involved atoms together. Right. Now I know in ionic bonds what is going to happen. I have a cation, right? I have a cation which is positively charged. I have an anion which is negatively charged, right? So I know positive and negative will attract. So that is the reason why they are together. This strong attractive force. This attractive force is nothing but electrostatic force of attraction, right? What kind of force of attraction exists in ionic bond? There is nothing but electrostatic force of attraction, because I have a full positive charge, full negative charge, so they will have some kind of attractive force. Obviously it is electrostatic. The force is what is called as electrostatic force of attraction. Okay, right? Fine. Now, what kind of molecules can form ionic bonds, and what are the properties of ionic bonds is the question. Right. Now you understand that an element, first metal, obviously, okay, fine. We've taken it, we'll generally say an element, right, has to form a cation. Is it not? And another element has to form anion. Another one has to form anion. Okay. Now, The conditions, what are the favorable conditions, right? Favorable conditions for ionic bond to be formed, right? Favorable condition for ionic bond to be formed is that the element which is forming the cation, right? The element which is forming the cation should have less ionization energy. Is it not? Is it not? That makes it very simple. If I have very less ionization energy, obviously removal of electron is very easy. Formation of cation is also very easy. Is it not? Right? Same way, this one, the another element is going to form the anion, right? Now it should have high electron gain enthalpy. Very simple. More electron gain in the sense I highly negative value of electron gain enthalpy. Hope you know what is electron. Lot of amount of energy is released when electron is added to that. Okay, right? So the two favorable conditions for ionic bonds to happen, right, is that the element forming the cation should have less ionization energy, right? And the other element which is forming the cation should have high negative value of electron gain enthalpy. If these two are there, yes, definitely cation is formed, anion is formed, and they'll be together because of the electrostatic force of attraction. Okay, now guys, we have to go back to the periodic table chapter. When I asked you when we missed anything, you said no, but we did miss something. What did we miss in periodic table chapter? Think about it and tell me. We missed one important thing in periodic table chapter. What did we miss? Let me see if anybody can catch that. What did we miss? You can go through your books if you want and tell me what we missed. I know what we missed, obviously. I now remember. Let me see if you can remember, or go through your textbooks and tell me what we forgot. I mean, what I forgot to teach you. There is one important thing we missed. What is that? Nobody remembers. Check your book. Open your books and check what we missed. Did we see anything? Did we see everything? The answer is no. I'm telling you, we missed something important. Something we missed. What is that something we missed? I'll give you a minute's time. 7 minutes. Okay, I'll give you 2 minutes time. Go through your textbook and tell me what we missed.
Sir, what is it related to?
It is not an atomic trend. Yeah, all the atomic trends we saw.
Is it about oxidation state?
Oxidation state? No, like oxidation state, we didn't. Maybe I didn't tell you because we didn't study about redox reactions yet. No, not that. Generally, elements in the same group only have similar properties, right? Is it possible for elements in two different groups can have same properties? I almost told the answer, what we missed.
Sir, diagonal relationship.
Diagonal relationship.
Exactly. Right. That is what we missed. Right. So we'll see that now. Okay, it'll take only five minutes. Let me complete that and then we'll come back to this. Okay. Right. So guys, we are going back to periodic table because we missed one important thing. We are going to study about diagonal relationship. Okay, so as I told, generally we have elements in the same group, some vertical column to have similar chemical properties. Correct, right? But sometimes it is possible for the element in one group and the next group, not like first group and 17th group, not so much difference, but say for one group and the consecutive one, the next one, some element can have similar properties. Okay, now there are pairs like this: lithium, then see, I know lithium, sodium is there, and then potassium. Here I'll have beryllium, magnesium, calcium. Lithium and magnesium are a pair, right? Same way, if I look at here, I have boron. Obviously, I have a gap here, right? Boron, aluminium, gallium, and then I have what is it? Carbon, silicon, germanium. You will see again boron and silicon, right? You have again similar properties for boron and silicon. There are similar properties for lithium and magnesium, so on and so forth. Only very few elements exist like this. Okay, even to some extent, aluminium and germanium also has. Okay, aluminium, germanium. Now you can write the pairs: lithium, magnesium, boron, silicon. Okay, boron, silicon, aluminium, and germanium. Right. So let's find out what are all the other things. Okay. So now what I want to tell you is that how is it possible? How is it that two elements in two different groups are having similar properties? What is the reason behind it? Okay, now the reason behind it is because all of them have similar sizes, or I can tell they have similar charge densities. Right, I told you what is the charge density. When I say charge density, CD, it is nothing but the amount of charge what they have divided by the size. That is what is called as charge density. Okay, CD charge density is equal to the amount of charge divided by the size of the molecule. When I say size, I'm talking about the volume. Okay, I'm talking about the volume, right? So now why do these elements, lithium, magnesium, boron, silicon, aluminum, germanium, why do they have similar properties? If someone asks you why is there a diagonal relationship, you have to tell them that they have similar charge densities, or obviously in little more crude way, right? I can tell that they have similar sizes. Is it not? Now, generally what happens when I go along, the period size decreases, right? But when I go down, the group size increases. So somehow lithium and magnesium have almost similar size. The same expression can be given for all of them. Okay. Now, how they behave similar, right? How they behave similar and all, if you ask me, I can tell that it will be in terms of, for example, I can tell in terms of reactivity, right? Say now, lithium and magnesium will not react with cold water. Cold water, no reaction, generally, right? But if I put hot water, they will react. Both of them will react. Okay, so like this, there are so many other things. And one more, say, for example, boron and silicon you take. Okay, if at all I have to give you, what are the similar properties? The oxides of boron and silicon are acidic in nature. Okay, the oxides of boron and silicon are a little acidic in nature. You will study more about them when I go for S and P block elements. You have S block elements, right, in this 11th class, right? At that time, we'll try to spend more time on that. We'll anyway study about group 1, group 2, group 13, group 14 in depth. All the elements, their properties, their chemical reactions, everything we'll see in depth. Okay, so at that time, we'll get more sense out of this. Okay, so now all you have to understand is there exists something called as diagonal relationship, in the sense that the element in the one group and the next element in the next group, the diagonal element, will have similar properties. And why do they have similar properties? Is because they have similar charge densities or similar sizes. Okay, and if someone asks you, okay, name at least one property similar between lithium and magnesium, you can tell always this: lithium and magnesium does not react with cold water, but they will react with hot water. Okay, and another thing you can tell is always about boron and silicon, or both their oxides are acidic in nature. And one more thing also I can tell: this aluminum and germanium, right? Aluminum and germanium are amphoteric in nature. What is amphoteric, people? What do you mean by amphoteric?
Sir, a basic as well as acidic oxide.
Sorry.
Both
Properties
basic
of
as
both
well as
basic and
acidic.
base.
No. It is, see, that is amphiprotic. H2O is amphiprotic, right? That means it can behave as an acid as well as a base. What is amphoteric? There's a subtle difference there, even though they tell that it can be both acid
Reacts
and this
with
thing.
both. Reacts with both.
That's the
acid and
correct
base.
point. Yes, correct. Who said this?
Srigiridhar.
Okay, Srigiridhar, yes, that's absolutely right. When I say amphoteric, that substance has the ability to react with both acid as well as a base. That is how you must tell. It is not like they can behave as acid and a base. No. They can react with an acid as well as they can react with the base. Those kind of substances are what are called as amphoteric substances. Okay, but molecules like H2O, that what you're telling is correct. They can behave an acid, they can behave as an acid, or they can behave as a base. How? It's very simple, right? H2O can accept H plus to form H3O plus. Now H2O can lose a H plus to form OH minus. Either of the way. Right? Anyway, so it can form H plus, it can produce, it can accept H plus. This is amphiprotic. This is the way they behave as a both, they behave both as an acid as well as a base. Okay, there's a difference between yeah, tell me.
Sir, can you once show that charge density is equal to charge by size?
Charge density is equal to charge by size.
What does charge here means? Does it mean the valency?
Yes, valency. The +1, +2, which we write. Yeah, that's what we mentioned here. Yeah. Okay, right. So yeah, this is the point which I have to do. So I wanted to tell you diagonal relationship. Okay, so I think we'll continue with your ionic bonds now. Any questions anybody has in this? If at all you're ready, this is not that important. They will just, if at all it comes, it will come in 1 or 2 marks question, right? If you're interested, please do read about it. Google it, right? Study it. Again, there are so many interesting facts you can get about these diagonal relationship. Google it and study if you're interested. And if you have any doubts, you can always approach me. I'll be able to help you.
Sir, how do we find volume of an atom?
How do we find the volume of an atom? Okay, that's a good question. I'm not sure, right? How do we calculate the volume of an atom? I'm really not sure. Maybe it is not to any instrument. No instrument can do it, right? I think it is purely theoretical, right? Say your Rutherford and all has predicted what is the volume of the nucleus, right? And somehow I even know what is the volume of an electron. Right, so I add up all these things. Maybe that's how I'll end up with the volume of an atom. That's how it is. Okay, but there is no sophisticated instrument. No instrument can do this. No instrument will be able to measure the volume, right? But I think it is all purely theoretical values, right? Purely theoretical values.
Okay, sir.
Right, but I'll also look into it. How exactly do they come up with a theoretical value? I will look into it. You also look into it. Okay, that's a very nice question. I'll also look into it. Right. Any other question anybody has? Okay, right. So moving on. So we were talking about this ionic bonds. As I told you, cation is there, anion is there. So they will have force of attraction. And what force of attraction? It is the electrostatic force of attraction, right? Because I have full positive charge, full negative charge. Obviously, there will be a strong force, strong electrostatic force of attraction will be there, right? And what is the favorable condition for ionic bond to be formed? The element forming the cation should have very less ionization energy, so that a lesser amount of energy is spent in removing the electron. And second thing, the element which is forming the anion should have very high negative value of Eg. You should not just tell high Eg value, right? You should tell that they should have high negative value of electron gain enthalpy. Okay, now these two conditions are satisfied. Yes, ionic bonds are formed. Right. Now, next thing what I have to understand or what we have to read or study is about the properties.
Sir, I have a doubt.
Yeah, tell me.
Sir, actually, let's take two elements, Na, sodium fluoride and sodium chloride.
Sodium chloride and?
Sodium fluoride.
You want to take sodium chloride?
No, sir, I want to compare the ionic strength between sodium fluoride and sodium chloride.
Oh, sodium fluoride. Okay. NaF and NaCl. Yes, absolutely. Yeah, tell me.
Yes,
okay.
sir. So if we see here, which has more ionic strength, so obviously electron gain enthalpy of Cl is more than F.
Yes.
But
yes,
still
yes.
NaF is more ionic
Absolutely.
than NaCl. Why is that?
Yes. Good question. There is this thing called as see. Okay, maybe I will maybe hold on to this thought. Okay, now we will answer this once we complete the covalent bond. Right, once the covalent bond is completed, then we'll come back to this question. This is actually there is this thing called as ionic nature in covalent bonds, right? Or say there is covalent nature in ionic bonds. Nothing is 100% ionic, 100% covalent. There is always a mismatch between these two. There will be some amount of ionic nature in covalent compounds. There will be some amount of covalent nature in ionic compounds also. Okay, we will answer your questions. Answer is obviously NaF is having more ionic. There is more ionic than NaCl. Okay, the reasons are there is something called as polarizability, polarizing power. All these things are there. Now this is included in your syllabus. Okay, we will answer those questions. Don't worry. Keep this in your mind. Okay. Right.
Okay.
So once we complete covalent bonds, of course, you have to understand how covalent bonds are formed. Then only you can understand how ionic nature exists in covalent bonds. Okay. So when you come to that, then or say covalent nature and ionic bonds, whatever it is, we will actually answer the question. Or we can actually, for our discussion, we can actually do it tomorrow itself. Okay. We'll study about first the ionic bonds, what are the properties of ionic bonds and all that, right? And we'll also see how some covalent character exists in an ionic compound. We'll try to answer the question. Tomorrow we'll answer your question. Okay, we don't have to wait for so long also. Tomorrow is the day. Okay,
Yes,
right? Right. We'll go step by step. You can now only starting and I will explain you, maybe you will understand, but maybe the other students might or might not be, right? So we'll wait, we'll just go with the flow just to have properly finishing everything and then going to that point. That always makes sense. Okay, right, fine. So now we will spend some time on properties of ionic bonds. Okay, properties of ionic bonds. Right, first one. The bond is, I would say, bond is very strong. Okay, generally, when I compare a covalent bond, right, compared to a covalent bond, an ionic bond is, this is again a general case, people, right? There might be a case where I have some covalent bond to be stronger than ionic bonds also. And one thing is there. Now, if you compare, say, any strongest of ionic molecules you take, okay, any strongest ionic molecule you take, and you compare it with this H, this is a covalent bond. Obviously, I know this is a covalent bond. Now, this is the strongest bond in chemistry. Okay, H bond, right? That is the strongest bond in chemistry. Okay, but again, in general, we can say that ionic bonds are generally stronger than covalent bonds in general. Why? Now, because there is no kind of charge coming into the covalent bonds. But here you see, this is a proper electrostatic force of attraction. I have a full positive charge, full negative charge. There is always a very, very strong force of attraction there, right? That is why we say that the bond is very strong generally. But again, there can be exemptions. There can be not only one exemption, there can be many exemptions. But generally speaking, ionic bonds are stronger than covalent bonds. But this is not always true. Okay, right. Next point regarding your ionic bonds is that ionic compounds will generally have high boiling points and melting points. Okay, ionic compounds will generally have high boiling points and melting points. Again, it is very simple. Why is it like this? It's very simple to understand because they have a very strong bond. Is it not? They have very strong bond between them, and that's the reason why they have very high boiling points or melting points. You know what is a boiling point, right? The temperature at which the liquid gets converted to gaseous state. Okay, same way, melting point is the salt get converted to the liquid state. At what temperature it happens? That is what is melting point. Okay, so generally, ionic compounds have very high boiling points and melting points, and why? Is because of the previous reason. Because their bond is very strong. Okay, third one is that they are highly polar molecules. I think this point we mentioned in the previous case, in the previous chapter, right? They are obviously highly polar. Now, as I told you, polarity is directly proportional to difference in electronegativity between the bonding atoms. This point I already mentioned. Right, polarity is directly proportional to difference in electronegativity between the bonding atoms. Okay, say for example, if I compare HF and HCl, if I ask you which is more polar, what will be your answer to this question? If I ask you HF and HCl, obviously HF is more polar, right? Because H and H same, but fluorine is more electronegative than chlorine. So the difference in electronegativity, delta En here and delta En here, here the delta En is greater. That is, the difference in electronegativity is greater in this case. So more is the polarity. Okay, so that's what I'm telling. Here, obviously, what I have here, I have electropositive element forming a cation, electronegative element forming an anion. Right, so obviously all these compounds, all these bonds, ionic bonds are highly polar, very, very, very highly polar. Okay, right. Fourth point is that they are highly soluble in water. Okay, all ionic compounds. Okay, all ionic compounds are hugely or highly soluble in water. Okay, now for this solubility, I want you to remember one phrase which you'll again be using in your 12th class, like dissolves like. Okay, like say, we'll think about this. I have sugar or salt for that matter. Take salt, table salt, you put it in water and you try to dissolve, it will dissolve. Right? Now you take the same salt, you put it in petrol, it won't dissolve. Okay, try that. Or oil, you put salt in oil and try to dissolve, it won't dissolve. Okay, but say you take grease, you know what is grease, right? The lubricant which we use. Okay, you take grease, you put it in say water, you try to dissolve it, it won't dissolve, right? But you put the same grease in petrol or oil, it will dissolve. Right? Why is it like this? Why is it that certain substances get dissolved in one solvent, but in another solvent they don't dissolve? Same way, some solvent and some solute will dissolve in this solvent, but not in this solvent. Why is there a mismatch like this? Right? For us to understand that, you need to understand what this statement says. like dissolves like. What this statement is trying to tell you is that if I have one type of substance, I talk about solute and solvent. Okay, if I have one type of solute, that solute will dissolve only and only in that type of solvent. If I have A type solute and I have a B type solvent, it will not dissolve. But if I have an A type solvent and I have an A type solute, then it is okay. Then they will dissolve. Okay. Now, sir, what are the different types we have? Don't worry, we have only two types. Right? One being polar, the other being non-polar. So that means what? If I have polar solutes, right? If I have polar solutes, they will dissolve only in polar solvents. Same way, if I have non-polar solutes, they will dissolve only in non-polar solvents. Or I would say they will dissolve more in non-polar solvents. As you try to increase the polarity of solvent, the dissolution process will also be less. Okay, so remember, polar solutes will dissolve only in polar solvents, non-polar solute will dissolve only in non-polar solvents. That makes sense. That is what you mean by this term, like dissolves like. One type will dissolve only in that type. Right? So now you understood, right? Why is it that these compounds are, dissolved in water, very highly soluble in water? Why? Because I know ionic compounds are already polar. Water molecule is obviously polar. I have a OH bond here. Is it not? I have a OH bond here. I have this del negative, del positive. All these things are there, right? Highly polar. Water is a highly polar solvent. Okay, water is a highly polar solvent. Okay, so now your ionic compounds being polar, your water molecule being polar, they will dissolve easily. That's why we say that ionic compounds are highly soluble in water. Okay, right. Any other point which I missed regarding your ionic compounds? They're highly polar, highly soluble in water, they are strong, high melting points, boiling points. Yeah, and obviously they're what?
The crystalline lattice structure.
Yes. There are two more points coming to that. Their aqueous solutions or molten states are conductors of electricity. Okay. Now remember that their aqueous solutions or molten state, right, can be conductors of electricity. We know what are aqueous solutions. When I dissolve NaCl in water, that has become NaCl aqueous solution. Right? Now their aqueous solutions or molten state is nothing but the liquid state. Right? In both these states, they are good conductors of electricity. Okay, I think we already spoke about this. For anything to be a conductor, right? For anything to be a conductor, I should have some free charges, in the sense that there should be some amount of charge which should be able to move inside the conductor. Okay, only if there is some movement of charge, then only they can conduct electricity. Okay, so now if I have normal metal, say this is iron, I know is a very good conductor. Now obviously I have electrons in iron that will move this side, that side, whatever side. That's why it's a conductor. Now here, the charge carrier is electron. Okay, but understand, when I go for ionic compounds, whether it's an aqueous state or a molten state, right, the charge carriers here, right, the charge carriers here are ions, that is cations and anions. All I need is the charge. In what form doesn't matter, right? If I have some charge and if it is able to move inside the conductor, then if it is able to move inside the particular material, then it's a good conductor of electricity. Okay. Now, in case of metals, general, I have electrons moving around, so they are good conductors. In case of aqueous solutions of your ionic compounds, there the ions are the charge carriers. Those will move inside the solution. That is responsible for being a conductor of electricity. Okay. And last, and yeah, tell me.
Sir, even non-metals have electrons, then why don't they conduct electricity?
Exactly. It's not about having electrons. It's about having electrons which are free to move. That's the point. It should not be that tightly bound. Generally, metals can easily lose electrons, right? So now they will be outside the atom now, that electron. That electron is not tightly bound by the nucleus. So that electron can easily move. Yes, makes sense?
Yes, sir.
Okay, right. Now the last point, right? Last point is that they form highly ordered crystal structure. Okay, you know, obviously NaCl has crystal. Every ionic compound will have its own crystal structure. Okay, now this crystal structure can also be called in a technical word. It's called a lattice. Okay, so when I say a lattice, okay, a lattice is nothing but a crystal structure. You will study about these. What are the different types of structures we can have in your 12th class? There is a chapter called as solid state. Right, that's that. I think that is the first or second chapter in your 11th and 12th class. So you'll be studying about these, what kind of structures, what are the different parameters you can work on. All these things you'll be studying in this chapter, solid state. Okay, so they form a very highly ordered, and I say not ordered in the sense very highly, like say how we build a house properly. This room should come here only, in that room should have attached bathroom, kitchen should be facing that side only, highly ordered manner we plan, right? So like that, all ionic compounds will have a very proper crystal structure. That's why we mean by they form highly ordered crystal structure, and that crystal structure can also be called as lattice. Okay, and one more point also I can add to this. All these crystals will form the lattice, and all these lattices have very high lattice enthalpy. Okay, lattice enthalpy is nothing but the energy required to break the lattice. Energy required to break the lattice, in the sense that if at all you want to break the structure, you have to spend a lot of amount of energy, because that structure is very strong structure. Okay, so what do you mean by they have very high lattice enthalpy? You have to spend a lot of energy on the lattice for you to break the lattice. That is what you have to understand. That is what you mean by lattice enthalpy. They have very high lattice enthalpy. Okay, right. Fine.
Sir?
I think what is, yeah, tell me.
Sir, actually, in reality, isn't it the river? That is the energy which is built when a compound is formed.
Absolutely, yes. The proper definition of lattice enthalpy is, it is the energy released when the lattice is formed, or when the energy required to break the lattice. Both of them will have same magnitude, but different signs. Because one is energy getting released, another energy getting absorbed, but the amount is same. When a lattice is formed, that is the same amount of energy is released. If you want to break the lattice, you have to supply that energy. So yeah, both the definitions are correct.
Why did they change the definition?
No. I only changed the definition. They didn't change the definition. It is the energy required to break the lattice, or in other words, I can even include the definition here also. It is the energy released when the lattice is formed.
Even in book, it is given energy needed to break the lattice.
No. Both the definitions are correct, right? The magnitude will be same, but except that the sign will be different. No, don't worry about it. Okay, but proper definition would be this. I would say more apt definition would be this: energy released when the lattice is formed. That will be a better picture. But yeah, both the definitions are absolutely right. There is no partiality here. Both the definitions are correct. Okay, right? So guys, I think these are all the properties, 7 properties we saw for your ionic compounds. All these are very easy, right? One thing is connected to the other one. Okay, so I think we'll stop with this for today. Okay, is there any question anybody wants to ask me?
Sir?
Yeah.
Sir, so if we think this, like if we think in this logic, then we can say like ionization energy is equal to electron gain enthalpy.
No. Ionization energy is equal to?
It will be equal to the electron gain in enthalpy if it has a negative sign, right?
Not necessarily, right? I mean, that those two are entirely two different processes. The parameters involved are also very, I mean, what to say, very different, right? Say now, if I have to remove an electron, okay, first thing is I have to overcome the force of attraction, right?
Yes, sir.
Okay. But that thing is not even there. Like you don't have to, like, say, it's not like when you put the electron there, the nucleus is going to automatically going to attract the electron. It's not exactly the same. No, it is not. Okay. And say there, in case of ionization energy, it can the only way it can be existed, it can be a positive value. You have to supply it for sure. Right, but electron gain enthalpy, it's not like that, right? Whether it, depending on what the situation, whether it is becoming stable or not, or whether there is a lot of repulsions or not, it might be positive or negative. That time itself, it's gone. You can see it can be either positive or negative electron gain enthalpy. That point itself, you can understand that these two are not the same. Electron gain enthalpy and ionization energy not the same. But this, yes, this you will have more sense when I go to thermodynamics again. Don't worry. We'll study about lattice enthalpy. Wherever you see this term enthalpy, right? Wherever I wrote this term, whenever we spoke about energy, you will get a clear-cut idea when you go to thermodynamics. Don't worry. Okay, these two are same. Okay, don't worry about this. Right? Yes. Any other questions anybody has?
Sir, is bond and electrostatic force the same?
One of the possibilities of a bond is an electrostatic force. Ionic bond is an electrostatic force, but covalent bond is not. Covalent bond is not an electrostatic force. No. That is
so
different.
electrostatic force is a bond, but bond is not an electrostatic force.
Yeah, bond can be an electrostatic force, but saying that bond can only be electrostatic force is wrong.
Yes,
Like
sir.
I get me. Okay. Yeah. Good. Any other questions anybody has? Okay, fine. Then if that's the case, we'll stop right here, people. We'll meet you tomorrow. Okay. Oh, it became so dark. I didn't realize. I'm so sorry. I should have put the lights. Okay, I'm sorry. It's fine, people. We'll meet tomorrow. Thank you so much.
Thank you, sir.
Thank
Thank
you,
you.
sir.
Thank you.
Thank you, sir.